Greetings, everyone. Um, in the corner of my whiteboard at school, I have Euler's identity or Euler's equation on the board, and I always tell the BC students that after we get through with the series stuff, I will derive for you where this comes from, or I'll prove it to you. Just as a quick side note, there are a lot of people who think that Euler's identity is the most beautiful equation in math or science. And some of you may wonder, well, how is an equation beautiful? Well, one thing you have to keep in mind is that beauty is in the eye of the beholder. But if you just look at this, you have, the simple, standard for our number system, the numbers 0 and 1. Um, and then you have these transcendental numbers, e and pi, that come up, and the complex number, complex unit, I, all related in this very simple, easy to read equation. It's kind of a marvel that they are related to each other in this way. And so it gets elevated because of that relationship. But we want to understand where it comes from. So to understand where it comes from, we're going to need to look at the Maclaurin series for a couple of functions that we became familiar with. So let's recall that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 plus x to the n over n factorial plus dot dot dot. So it's a Maclaurin series for e to the x, or the Taylor series centered at 0. Let's also take a look and recall what the Maclaurin series for sine is. For sine, remember, sine is an odd function, and so we have all the odd power terms. So we're going to have x minus x cubed over 3 factorial plus x to the fourth over 4 factorial. What am I talking about? This is where my brain is doing one thing in my, it should be x to the fifth over 5 factorial. My mouth is doing something different. Minus x to the 7 over 7 factorial plus dot 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 plus negative 1 to the n, x to an odd number, 2n plus 1, over that same odd numbered factorial. And then one more, cosine. This is the even function, so these are the even powers, so 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and then plus dot 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 plus negative 1 to the n, x to the 2n over that even number 2n factorial plus dot dot dot. Now, if you just look at these three Maclaurin series, you should be able to see that they kind of overlap a little bit. The terms of e to the x seem to be created by the terms from both sine and cosine. At least if you took the magnitudes of the terms, the magnitudes of every term from sine of x plus the magnitude of every term of cosine of x, add those together, and you get e. So there's some connection here that we have to make, and in doing so, we'll end up with Euler's identity. Let's do another little thing. Let's do a little bit of a recall from an earlier class when you learned about the complex numbers. Specifically, you should recall that I is the square root of negative 1. Now, if I square I, that means I get square root of negative 1 times the square root of negative 1, and we get negative 1 out of that. Okay. What if I cube I? Well, I cubed is just I squared times I, and I squared is negative 1, so I cubed is negative I. What about I to the fourth? Well, I to the fourth, excuse me, is just I squared times I squared, negative 1 times negative 1, which is just 1. What about I to the fifth? Well, I to the fifth is just I to the fourth times I. I to the fourth is 1, so that goes right back to being just I. What about I to the sixth? Well, that's going to be, there's a number of ways you can think about it, but it's I to the fourth times I squared. I to the fourth is 1. I squared is negative 1, so this is negative 1. And then what about I to the seventh? Well, again, we can take out that I to the fourth, and then this is going to be I to the fourth times I cubed, or 1 times I cubed, which is just negative I. Just looking right over to the left there. And then I to the eighth is just I to the fourth squared, if you will look at it that way, which is just 1 squared, or we're back to 1. And it's going to keep cycling like this as we keep going forward. You probably at an earlier class were asked to evaluate or simplify I raised to some large power. And this is what you were doing. You're essentially finding the remainder when the exponent was divided by 4. And when whatever the remainder is, then you got one of these. All right, so how do we incorporate that into this? Well, we're going to look at the exponential Maclaurin series here, except we're going to look at it for the input I theta. Theta is just an angle measure, okay? And so, well, let's put this into the Maclaurin series. It's 1 plus x, so it's 1 plus I theta plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial, and then that's going to continue. I'm not going to worry about the general term for this. I'm just going to just observe I see a pattern here. And let's go ahead and simplify this a little bit. So this is 1 plus I theta. There's nothing to simplify there. When I take this, the third term here, and I square I, remember that's going to, I squared is -1, so that's going to make this negative. And then I'll have I squared over 2 factorial. When I raise I to the third power, that's going to make negative I, so I'm going to have a minus I theta cubed over 3 factorial. In fact, I can scroll down a little bit so you can see that. Remember, I cubed was negative I, so I'm just replacing I cubed with negative I. I to the 4th is 1, so I'm going to get plus theta to the 4th over 4 factorial. Let's put a few more of these in here just to see the pattern here. I to the 5th is going to be I, so I'm going to have I plus I theta to the 5th over 5 factorial. I to the 6th is -1, so I'm going to have minus I to the 6th over 6 factorial. I to the 7th is negative I, so I'll have negative I theta to the 7th over 7 factorial. I to the 8th is back to 1, so I'll have theta to the 8th over 8 factorial. And then this is going to continue. And if you notice, we have 1, and then a plus. So a plus, plus, then minus, minus, plus, plus, minus, minus. 2 positives followed by 2 negatives, and so forth on down the line. Also notice that some of the terms have an I in them. Which ones? Well, it's all the ones that have an odd exponent and an odd factorial in the denominator. None of the ones with an even have that. Okay. That's interesting. Let's go ahead and gather those terms together, those with an I and those without. Let's put those with without an I first. So let's do 1 doesn't have an I, minus theta squared over 2 factorial, and then plus theta to the 4th over 4 factorial, minus theta to the 6th over 6 factorial, plus theta to the 8th over 8 factorial, minus dot, dot, dot. I don't need a general term here, but that's what I got. I'm just going to continue. Plus, now all the terms that have a factor of I, I'm just going to factor that I out here. And then what am I left with? I'm going to have a theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial plus dot, dot, dot. And that's going to continue forever. Well, what do I have here? All the even exponents here alternating in sign. This is cosine. This is cosine of theta. What do I have over here? All the odd exponents alternating in sign. This is just sine of theta. That's the Maclaurin series for sine evaluated at theta. So e to the I theta can be rewritten as cosine of theta plus I sine of theta. That's a cool relationship in and of itself. So we only have one more step left for this. Now we're just going to replace theta with pi, since theta was an angle measurement, or just a real number, really. And we'll use pi as our angle measure, or number. And so what does this become? This becomes cosine of pi plus I times the sine of pi. And if you recall, cosine of pi, that's just -1. Sine of pi is 0, so plus 0, which I'm not going to write. So e to the I pi is going to be equal to -1. So if I just add the -1 to both sides, so I get e to the pi I plus 1 has to be equal to 0. And there we go. There's Euler's identity. Falls out of a combination of the Maclaurin series for E, for cosine and sine, using the complex unit I, or the square root of -1. That's a cool relationship. I hope you enjoyed that derivation because I think it's really cool for you to see that. Go study.